So in the last video, we presented some rules for being able to evaluate sequences that commonly occur. And now we want to present 4 general methods that we can use when we encounter sequences that don't fit into one of these nice forms. And the first is a rule that you're already pretty familiar with. It's basically using the squeeze theorem. So it says if we have 3 real sequences and we know that the sequence elements xn is less than or equal to yn is less than or equal to zn for all n, or that this inequality is eventually true, right? There's some capital N such that once you get past that, the capital Nth term, this inequality holds. Okay, and these two sequences on the outside both converge to the same number, then this squeezes or forces the sequence between them also to converge to the same number. And so just as a simple example to show how we want to use this, perhaps, suppose we wanted to look at the sequence sine n over n. Notice this doesn't fit into one of the forms, okay? But we do know that it's bounded between minus 1 over n and 1 over n. So we do know that this is true. And we know that this sequence converges to 0. We proved that earlier. And actually in the last video, we showed that if we know that a sequence converges, then we multiply it by a scalar, it converges to the scalar times the limit. So we know that negative 1 over n, that sequence converges to negative 1 times the limit of the sequence, which is 0. And so now we have what we want. We know by the squeeze theorem that this sequence also has to converge to 0. Okay, so that's this is a very useful result. Okay, the second rule is also very useful. It's a rule sometimes called the continuous function theorem. And what it says is this. It says if we have a real sequence that converges to some number c, and f is a continuous function of c, then if we form a sequence where the terms in the sequence are the function evaluated at the terms in our original sequence, that converges to the function evaluated at the limit of that sequence. In other words, here's kind of one way of thinking about this in a kind of loose sort of way. It basically says that this limit distributes. The reason why it's true is because if you think about what a sequence itself is a function. And so this is talking about the limit of a composition of functions. And we have previous theorems that tell us that this sort of result is what we should expect. Let me give you a simple example. Suppose we want to look at the sequence of the quantity n plus 1 divided by n square root of. Okay. We can show that this sequence is bounded above and it's monotonic decreasing. So we know that this sequence converges by the monotone convergence theorem. And now we notice something else. We notice that if we look at the argument of the square root, if I let a and b equal to n plus 1 over n, of course that's re-expressed as 1 plus 1 over n. And I know that the limit of a constant plus the sequence is going to be equal to the constant plus the limit of the sequence. or if we write all this out, and this will be equal to 1 plus the limit of 1 over n, which we know is 0. Okay. Now notice that if we define f of x as being the square root of x, we notice a couple of things. We notice that f is continuous at 1. Therefore, by this theorem, if we now look at the sequence if we look at this sequence, okay, we know that its limit converges to f of the limit of the argument, which is 1, which is equal to the square root of 1, which is 1. So it's a very useful theorem. We have another result that occurs when we can't directly evaluate the limit. And we saw some of these cases before. We had these forms of infinity over infinity, 0 over 0, and we had to use Lhopitals Rule. And here it turns out that we can use Lhopitals Rule for sequences too. So if we write the sequence literally as the function, then the limit of the sequence is the limit of the function, okay, as x goes to infinity. And let me kind of illustrate this. Suppose, for example, we go back and we look at one of those limit laws we had before. Recall that we saw that the limit as n goes to infinity okay, we made that claim. Now we want to prove it. So what I'm going to do is the following. I'm going to write this sequence. I'm going to say f of n is equal to, okay, this is going to be the function that generates the sequence. And what this tells me, therefore, is that the limit as n goes to infinity of the sequence is equal to the limit of the function as x goes to infinity. And we notice that the form of this limit is an indeterminate form of infinity over infinity, so we can apply Lhopitals Rule. So this will be equal to the limit as x goes to infinity. The derivative of natural log is 1 over x. The derivative of x is 1, and so we're going to get 0. This is by Lhopitals Rule. Therefore, it follows that the limit of the sequence is 0, just as we claimed earlier. Okay, now we come to the last rule. This is a fascinating rule. It's a rule for evaluating limits of convergent recursively defined sequences. And what I want to do is I want to go back to that recursive sequence we had before. So this was a previous example we had. We said, okay, we were going to let the first term be equal to 1, and then we recursively define the sequence like this. And we showed that this converged by the monotone convergence theorem. We showed that it was bounded below by 0, above by 2, and we showed that it was a monotonic increasing sequence. So we know it converges. The question is what to? And here is what we're going to be able to say. So this is our theorem here. If we have a recursive sequence like this, which we know converges, then we can take the limit of all the terms in this expression. Okay. And normally this f is going to be continuous. So if we assume that this converges to C, it automatically follows that C is equal to f of C, and we can solve for C. So basically it says when we have a recursive sequence that we know converges, we can just take the limit of all the terms in that expression, in that recursive expression. And let me illustrate with this example. So in our example, basically what we're going to do is we're going to let the limit of yn be equal to c, because we know the sequence converges, so we're allowed to write that. So therefore, it follows that if we go back to our expression, I'm going to take the limit of both sides as n goes to infinity. Notice the limit of yn plus 1 is the same as the limit of yn, right? This is a continuous function. So the square root function is going to be a continuous function. Therefore, the second method that we presented said you can just basically take the limit inside. This is by the continuous function theorem. Therefore, we get the result that c is equal to 2 plus c square root. And we just solve for c. Square both sides. And of course, we're going to get two roots. C is equal to 2, C is equal to minus 1. We know that it can't converge to minus 1 because the whole sequence is bounded above by 0. Therefore, this has to be the limit. And it's not surprising because we knew it was bounded above by 2 and it was monotonic increasing, so it makes sense that it could converge to 2. Okay, so those are the methods that we're going to use when we don't have one of those nice forms that we had in the previous video. And the next video is going to present some practice problems for you to try and to kind of see how to use these rules.